A very warm welcome to all of you. I, Akash Sharma, on behalf of MIDAS IT, welcome you all to the webinar series on slope stability. So, this is our slope webinar series schedule. First, today, that is March 4th, we are taking the topic of slope stability analysis, the theoretical background and introduction to SoilWorks slope module. And in the next webinar topic, we'll be taking the practical application where we'll be designing, we'll be coming up with the design of an particular field project with a particular problem statement. So for today, this will be the workflow. First of all, I would be starting with introduction to slope failure, its application. Now, what are the method of analysis available? Like LEM, SRM, SAM, their theoretical background, how do they work? Categorization of problem into 2D and 3D, where one can go for 2D analysis, where one can go for 3D analysis. Brief introduction to SoilWorks, its advantages. Case study, a plane strain problem. So basically, I will be completely dealing with the workflow of SoilWorks so that in the next webinar, you don't feel any problem while dealing with the practical application of the same. Slope failures. Now, slope failure has recently increased in number considerably with the advancement of infrastructure on or near slope, bringing heavy loss to life and property. Now, what are the application areas or what are the application areas where you need to go for stability check in case of slope? For example, when you are reinforcing a cut slope, now analysis of reinforcement for minimum factor of safety, considering dry and rainy season condition, that is very important, and also stability check reflecting the rainfall intensity. So this is the first application. Then reinforced earth retaining wall. Now stability check for reinforced earth retaining wall. Now which should reflect the various practical reinforcement material considering both dry and rainy season conditions. Then slope stability at the tunnel exit, considering the stability for both sides of slope. Abutment pile foundation on slopes. Nowadays, as you know, that abutment pile combination is used with because of the effectiveness of pile to deal with the horizontal forces. Now here you should be able to do the construction stage analysis, now reflecting excavation and backfill, because in soil it plays a very important role when you go for construction stage analysis, and thus you can study the effect of pile abutment system on the stability of the slope. Next is the dam leaves with cutoff wall. Now the pore pressure in dams embankment should be considered in slope stability analysis. And this point I would like to underline once again that the pore pressure, I'm not talking of the gamma saturated. The pore pressure variation in the dams and embankment should be considered while you are doing the slope stability analysis. That is, a seepage slope coupled analysis should be possible whenever you are doing an analysis check for dams and leaves. So these are the application areas. Now what is the solution to the slope failures? The solution to the slope failure is that proper stability check before construction whenever you are going on or near the slopes. Okay. So what are the various method of analysis? Now first is the limit equilibrium method. All of you know the simple circular arc method like Bishop method, Fellenius method, and the second is the strength reduction method, which is nothing but a finite element analysis where the strength is reduced to get the factor of safety. Both of them I will take in detail now so that you can understand how exactly it works or what is the background analysis for both these methods, talking about their advantages and disadvantages. Now, first is the limit equilibrium method. It is the traditional method of analysis based on simple equilibrium condition, which is considered in almost all the codes. So here we do nothing but what we do is that the soil mass is divided into a series of vertical slices. As you can see that it is divided into a series of vertical slices, and then the stability or the equilibrium of this particular slice is considered about an assumed center of rotation, which is O in this case, as you can see on your screen. Okay, so now by examining the moment equilibrium about that center of rotation, now two expressions are derived for factor of safety. That is the SR, that is the shear strength of the potential failure plane, and SM, the total mobilizing forces acting on per unit area of that plane. But in simple words, I can just say that if this is my slice, then what are the forces which are making it fail and what are the forces which are opposing the fail? So the factor of safety is nothing but the ratio of both. So this method is based on simple equilibrium conditions. Now, as you can see in that, but in the previous slide, that there are a lot of forces to be considered. Now, the thing which happens is that when you have a lot of forces, the equation becomes indeterminate. Now, to make it determinate, we have to make some assumptions. For example, in Felenius method, the interslice forces X and E is not considered or considered as 0. Same in Bishop's simplified method, the interslice force is horizontal, that is X is not considered. So similarly, you have to come with an assumption in this particular type of analysis to get the factor of safety on the equilibrium basis. Okay. Now next, let us come to the theoretical background of finite element method, which is the strength reduction method. Now in strength reduction method, it is a method which simulates the actual slope behavior mechanism and determine both the factor of safety and the failure behavior. Now I'll tell you how exactly it works. For example, you can see on your screen that there is an embankment and I'm just considering an element A. Okay. Now the initial strength parameters or the initial stress condition of this if this element is nothing but tau is equal to C plus sigma tan phi, where C and phi determines its strength parameter. When plotted, you can see that left below the first figure, the first graph, you can see that this is our first line and this is the Moore circle criteria for that particular soil. For that particular failure condition. Okay. Now what the program does is that this is C value, right, and the phi is that angle. Okay. So what the program does is that it goes on reducing the C and phi value. Okay. It is being reduced till it fails. Okay. Then the program fails similarly other elements till it comes with a failure plane. Okay. And then based on this, the factor of safety is calculated as tau upon tau f, where tau is nothing but the shear strength of the slope material initially. Okay. Then tau f is nothing but the shear strength at the time of failure, and thus the factor of safety is calculated. Now you might be thinking that what are the advantages of both the methods. So first of all, talking about limit equilibrium method, it is the most common type of analysis till now. So all the technical papers, all the codes, they give their criteria of stability based on this method. The analysis time required is very small and the relative ease and transparency in their formulation. For example, if you come up with a particular failure plane, then you can check it manually also whether your calculation or whether the software calculation is correct or not. Now what is the disadvantage with this method? It involves assumption regarding the failure plane surface, that is, it assumes it to be circular in nature. Involves assumption regarding slice side forces to make, as I already showed you, that to make the equation determinate, it have to make some assumption. And in the results, what you get is only the factor of safety. Just the program will say the factor of safety is 1.2. That's it. It will nothing tell you more than it. Okay, and it is not effective for 3D problems. Okay. Now talking about the strength reduction method, first of all, no assumptions, whether it be regarding the failure plane surface or regarding the slice side forces, there is no. And also in the post processing, it gives you the stress condition in the model, the horizontal displacement, the shear stress, the stress in the XX direction at the time of failure in the model. So a proper simulation of the ground condition could be done, and also it is effective with both 2D and 3D problems. Okay. So the disadvantage, if we see that no well-defined failure surface is there, means what you obtained is based on the horizontal displacement or the total displacement, you get contours, and on the basis of that you have to select your failure plane. requires extensive meshing for reliable results since it's finite element based, and analysis time is comparatively high because it has to do a lot of iterations to bring the whole model to failure conditions. Okay. Now, if you see the previous two methods, for example, in LEM, we were obtaining only the factor of safety as post-processing results. And in strength reduction, we do not have any failure surface, well-defined failure surface, I will say. So SoilWorks also provide you with a method called stress analysis method, where what is done is that stress analysis is carried out using the finite element on a surface which is defined using the LEM, that is the failure plane, or the circular plane is defined as in the limit equilibrium method, but the factor of safety is calculated using the shear strength of that particular surface. So this is a third method of analysis. Now, next is the categorization of problems. So when should we go for 2D modeling and when should we go for 3D modeling? Now, 2D modeling is preferred for plane strain problems, that is if the Z dimension of the problem is very large, and it can be assumed that the state existing in the XY plane holds for all the plane parallel to it. That is, the displacement of any XY cross section relative to any parallel XY cross section is 0. Okay, so as you can see in the figure, such kind of problems could be modeled as plane strain problems. But when the problem becomes such where like you do not have each section resembling the previous section, then you have to use the other method, which is the strength reduction method, and the modeling should be a 3D type of modeling. Now I'll just introduce you to the MIDAS 2D solution, which is SoilWorks. Now SoilWorks is all-in-one 2D finite element analysis and analytical software. For structural and geotechnical engineer, it has fully integrated pre, post, and solver. Now MIDAS SoilWorks is divided into 7 modules, which is slope, rock, foundation, dynamic, seepage, soft ground, and ground. Okay. Now in the slope module, you can perform the slope stability analysis. In the rock, basically you can also perform the slope stability analysis, which we'll be taking in the next webinar. Basically, when we deal with rock, there is not always the plane failure kind of situation. There could be a wedge failure kind of situation. So for that, we have separate module called rock module, where you have different constitutive models like Hoek, Brown, and others to simulate the rock behavior. And you can also consider a 3D analysis of a wedge failure kind of situation. Okay. Next is the foundation, where you can perform a PY nonlinear analysis for a group of piles. Then you have the dynamic analysis, where you can perform the transient time history, eigenvalue and response spectrum analysis. Seepage, where you can perform the steady state as well as the transient state analysis. Then you have the soft ground, where you can check for the consolidation. And then you have the ground, where you can perform the construction stage analysis for problems like shoring and tunnels. Now the most important part, like what kind of analysis can we perform? So I will take them in detail. First is ground. Now in ground, basically, as I told you, you can perform the construction stage analysis. So as you know that whenever we deal with soils, with each stage the stress in the soil changes, which affects our next stage. So one should go for construction stage analysis, and it becomes very much effective when you deal with tunnels and shoring excavation. Then you have slope. As I already told you that you can perform 3 analysis: SRM, SCM, and LEM. So here in SoilWorks, you can perform all the 3 analysis and make sure that your particular model, like as you know that in LEM there is a lot of assumption. So you can look in the same model from 3 types, from 3 views, and just make sure the proper stability of your problem. Then you have rock, where once again you can perform LEM analysis, and also you can check the same for wedge failure, like for a 3D kind of situation. Then you have soft ground, where you can perform 1D consolidation analysis as well as finite element analysis, which is basically a 2D analysis. Then foundation, You can perform the PY nonlinear analysis, seepage, steady and transient. Then finally you have the dynamic, where you can perform eigenvalue, response spectrum, time history, 1D equivalent linear analysis. Now the next I will show you the seepage slope coupled analysis, where you need the two modules, that is slope and seepage. If you remember in the initial in the first few slides where I was talking about dam leaves, I told you about that you should be able to consider the pore pressure variation in the dam. So MIDAS provides you with this option where you can perform the seepage slope coupled analysis. I will go in detail when I will come to the next slide. Then you have the soft ground slope coupled analysis. This is similar kind of situation. I will take this both this coupled analysis. I will explain it to you in detail later on during the presentation. So these are the 7 modules, the various kind of analysis and the various kinds of geotechnical problems which you could perform in SoilWorks. Now today I will just make you familiar with the workflow with SoilWorks, so that in the next webinar you do not find any difficulty while we deal with the practical application of the same. So the workflow with SoilWorks remains very simple. First of all, you do the modeling, then you define the property, assigning of properties, meshing, boundary condition, analysis, case generation, analysis, result verification, and report generation. Okay, so I'll just move on to the software right now so that I can show you that how exactly SoilWorks make it simpler to go through the workflow. Okay, so this is basically the interface of SoilWorks. So I'll just say new project. Okay, so this is the workstree window. I'll just make familiar to you the interface. So when you start, you first need to define the initial parameters. That is basically what is the unit system with which you are working. So SI, CGS, FPS, or user defined. I'm just using kilonewton meter second for this particular model. Okay. So what we are going to do today is, I'm just taking a simple problem where I'm taking a colloidal soil of depth 3 meter, on which I'm going to create, or I'm just going to have a landfill depth of 3 meter, and I want to see the factor of safety from 3 kind of analysis, that what results I'm getting. Okay, so let us create the modeling part. So you can directly import any CAD file if you have any CAD file of DWG, DXF, DGN, or you can create the model in SoilWorks itself. It is very simple to use because all the AutoCAD commands which you are using in SoilWorks can be directly, which you are using in AutoCAD can be directly use it in, you can use it here. For example, I just go to geometry, I say line. So you can see that command is line, specify the first point. So I'm just saying 0, 0, enter, specify the next point 10, 0. So you can see the line created. Then specify the next point 10, 3. Then let's say 6, 3, and let's say 3, 6, 0, 6, 0, 0. So I've just created, I just say escape, and you can see that the basic diagram has been created. And most of the time we'll be dealing with 2D problems, so same command can be used to create any complicated problem. You have the other commands also, like you have the arc, circle, rectangle, and point to. Okay, now I'll just create a line to divide it into 2 parts. So I'll just input the value as 0, 3 and 6, 3. So the line is created. Okay, Now next, if you remember the slide, the next we need to define is the property. So this is basically our completion of modeling part, because in 2D it's very simple always. So we'll just go to limit equilibrium method, ground material property. Okay. Now you see the model type, Moore column, LEM, and elastic ground. Now what's the importance? If I have Moore column, then why Moore column LEM? Always remember that Moore column LEM is required when you are dealing with LEM. For example, if I'm trying to check it for both the models, for example, I want to check it for LEM also and I want to check it for SRM also, I have to define the same material property with different model type. Okay. For example, when you go for Moore column LEM, there is no requirement of E and nu value. You can see the main parameters are gamma saturated, cohesion, and friction angle. As you know, as I told in theory, that it's totally an equilibrium based, which is based on forces. Okay. Now this is Moore column. So when you go for example, go for SRM, you have to define the material property here. It will be more clear. I'll just show you how. For example, I'm going to database. SoilWorks provides you with a huge database of soil properties. Even if, for example, landfill layer, if it doesn't matches with your local ground conditions, you can just change it and you can just save it for your future reference. So you need not define it again and again, just saving your time. Okay. So I'm just using the landfill layer and the colluvial layer, and the model type is Moore column. I'm just saying assign. Okay, so the two I have assigned. So please remember, both are having the Moore column. So I need to define the E, nu, C, and 5 parameters. Then once again, I'm going to database. I'm changing it to Moore column LEM, and I'm taking the first two properties. I'm just saying assign. Close it. So we have defined the material properties. The next important thing is that we need to assign it. Okay, so always remember that while you are dealing with SoilWorks, the material properties is always assigned to the surfaces. So you have to create the surfaces. Now MIDAS provides you with the second smart function. The first smart function is smart modeling, where you can just import it from AutoCAD. The second is we called it as smart surface. You just go to smart geometry and say smart surface. Automatically the surface will be generated for your model. Okay, so this 7 smart features helps you quickly model your complete your modeling and get to the results and report. I will show you how. So this is the second feature. Now we need to assign the material properties. Okay, so whatever curve or whatever geometry you create, whatever material property you create goes to the left hand side work plane. For example, you can see the ground material property which we have created. I'll just expand it. You can see Moore column, LEM, LEM. Okay. Then if you have created any mesh set, it will go here. And similarly, if you have any layer set, it is just created here. Okay. So let us start with assigning of properties. Now, how easy it is to assign? Just select this particular surface. Just select that material property, drag and drop. Okay. So the property gets assigned. Similarly, select the top surface, say drag and drop. Okay. Now in this particular model, I'm going to do both the analysis. So what I will do, I will first complete for SRM, then I will proceed for LEM. So first you can see I have used the Moore column, and the next step I will go for LEM. Why I'm selecting Moore column first or the SRM first? That because the material is, when we meshed it, the material is assigned to the mesh. No meshing is done in LEM, so it is retained by the surface. So first we do the SRM. Okay, so next we need to mesh the model. Now meshing becomes very important. People are very reluctant to use finite element analysis because meshing, where to keep it fine, where to keep it coarse, is a very big question while you work with finite element software. Now the third smart function is nothing but the smart mesh. You just go to model. You'd see that you have the other option like auto mesh, map mesh, grid mesh, where you can manually control your mesh. But for a new user, you can directly go to smart mesh, say what kind of refinement you require. For example, you require very fine mesh or coarse mesh. Just say the program. I'm just saying fine mesh. Generate high order element because it is recommended to use for SRM method. Generate triangular elements and just say OK. Okay, so automatically you can see that the program will automatically consider finer mesh over here and coarser mesh here according to your refinement. So you can see that whatever mesh set you have created is created with name, colloidal layer and landfill layer, and you just need to activate, deactivate in the analysis case. Now the next step is providing the boundary condition. Now providing the boundary condition is not a big task in 2D. You just need to select the curve and provide the restraint accordingly. But with the smart functions, it becomes very easy. You just go to load boundaries, you just say smart support, you just give it a name, let's say GS for ground support, and just say OK. And the program will automatically give the boundary condition. So it is helpful, like for example, I'm changing my mesh size. Now each time I need to select the curves and then assign the boundary condition. Here you just say smart support, say OK, give it a name, and the program will automatically give the boundary conditions. Okay. So with this we complete our analysis case. Now if you want to have any kind of loading, like for example pressure load, you can just select the boundary curve or the curve and just give it some value 20. You can just preview it in which direction it's working. So let's say -20, preview. So it's fine. So you can say OK and use it in the analysis. Okay. For now I'll just generate the analysis case. So analysis design, say analysis case, say add. Method is strength reduction method. Use all mesh sets, use all boundary sets and the self weight. Okay. Now in the analysis control data, if you want to define the initial water level, let's say 2 meter. So it will be somewhere in the colloidal layer, because colloidal layer is 3 meter thick. Just say OK, give it a name, say SRM, and just say OK. So what we have done is we have just completed one analysis case for SRM, or the finite element method. Now I will quickly show you how in the same model we can generate the analysis case for SRM as well as LEM. So now the mesh is not required because it's a simple equilibrium method. It's not a finite element method. Okay. Now once again we need to assign the material properties. Similarly, just select the surface, drag and drop, select the surface, drag and drop. Okay. So next, if you remember, was meshing, not at all required. In the boundary condition, you need not support it because it is not at all required. What we need to define is we need to define the center of rotation and tell the program how it is going to calculate the arc failure surface. So that is the boundary condition for me in limit equilibrium method. So I'll go to limit equilibrium method. I will say arc failure surface. I will give it a name. Let's say arc failure. Okay. Now draw the grid range. So you can draw any bigger size of grid because the analysis time is very less. So I'm just drawing an arbitrary grid. Okay. I can make it more finer. Let's say 0.25. So the grid is fine. Now these are nothing. These are just my center of rotation. If you remember in the theory part, I said that the stability will be checked about a single center of rotation. When we do it manually, we calculate for one single point. But the advantage of software is that you can create a whole grid of center of rotation, and from each grid the program will automatically calculate the failure surface and the factor of safety. Okay, so we have defined the grid range. Now next we need to tell the program how it is going to create the circles. Okay, so first there are 2-3 methods. Today I'm taking method of using arc radius. So method of searching the first arc radius. For example, if this is my center of rotation, any point you can take. Now how it is going to calculate the R0, or how it is going to calculate the first radius for the circle. So what the program will do, it will just draw a normal to the curve and it will take R0 as the initial, whatever the distance is. For each of the point it will calculate separately. Okay, what is the arc radius increment? If first is R0, then what is the next size of your circle? So I'm just saying 0.5. Number of arc from each point, so 10. Okay, so just say OK. So this is how you define. So here you have completed once again the part. You just go to analysis, analysis case, say add, select the method as LEM, use all layer sets. In the boundary sets you just need to activate the arc failure. GS is for the finite element support and the self weight. Okay. Now in the analysis control data, which analysis method you want to use? Bishop, Felenius, Janbu. So SOILWORKS provides you with all the analysis method, both traditional as well as advanced in the field of LEM. Which direction it is going to fail, left to right or right to left? I'm just saying left to right because in our model it will be failing this way. The initial water level, once again 2 meter, and just say okay. Okay, fine. Now I'll just create SAM also, because SAM I need not define anything separately. All mesh sets, because as I said that the stress analysis will be created. All boundary sets, because I have ground support, because I have to support this, and arc failure will be basically defining my failure surfaces, and all load sets. Okay, as I already told, it is nothing but combination of two. I'm just saying 2 meter initial water level, say okay, just give it a name SAM. So okay, so we have created the 3 analysis case. Now you need not do anything. In the design option you can say that what is your minimum factor of safety. This is basically for report generation. I'm just keeping it 1.3. Analysis, say analysis and report, perform analysis, just save the model and run the analysis. It will take some time, so I'll just show you the already analyzed model. Okay, so let us see what exactly we get in the results, because it is the most important part. So first of all, SRM, you can see that the factor of safety is 2.53. so let us see the displacement. So this is my displacement. Okay, now based on this I will define my failure surface. So it could be the red one, it could be the yellow one, or it could be the green one. So it is based on my assumption that what is my factor of safety I have to determine. For example, I'm getting 2.53, which is safe enough for now. But if it was 1.2, then which area I'm going to reinforce? Because in the second webinar I will show you that how we select that particular area and we reinforce that particular area. But this is how we get the results. What is the vertical displacement and total settlement? As I was telling that, you also get that what is the stresses in the model at the time of failure. Okay, so this is about SRM. Then we'll talk about LEM. Now as I told, in LEM what you get is only the factor of safety. Okay, now if you check in this model, from each point it has tried to draw the circle as per what we have defined, and what we get is this as the failure plane. So you can see it in red color, whichever is the minimum. For example, 2.4965, fine. And this is the slices. Now you can double click on each of the slices and you can see that what value it is taking. For example, what is the slice width, what is the C value, phi value, pore pressure, and how it is taking into consideration the same thing while considering the equilibrium condition. So you can check it for each of the slice, and the calculation which we used to do manually is automatically done by the program. So you can make sure that now you have selected the most critical surface. Now it's very much clear. If you can see that the failure surface, which is as shown by LEM method, can be very much related to the horizontal displacement of the SRM method, but it helps you to check the method, check the model from 2 different perspectives. And then finally you have the SAM method, which is, as I told, is basically nothing, the same method, so almost the same factor of safety, but you can get what is the basically the stress condition in the model once again at the time of failure. Okay, so which is 2.5432. okay, so one more advantage with SOILWORKS is that it automatically generates a first-hand report for your model. For example, you can see that is list what is the objective. As I already said that in the design option we kept it as 1.3. So user defined. Then what are the properties which we took? What are the results from each cases, and different images taken automatically by the program. Okay. So now I'll move on to the presentation part. So what is the advantages with SOILWORKS? First of all, different analysis for the same model. You can check the model from 3 different analysis method and hence ensure safety for the slope which you have designed. Construction stage analysis. Now it helps in simulation of really construction sequence and study the influence of its effect on the slope stability. For example, in the figure, as you can see, we are performing a excavation. So you can perform the construction stage analysis and you can check that for each step what is the factor of safety we are obtaining, both with the help of limit equilibrium as well as strength reduction method. Now next is the seepage slope coupled analysis, which I told that I will discuss in detail a bit. Now the thing is that when we define the water level here in the slope module or any other program, what it considers is that it considers while doing the slope stability analysis the gamma saturated that is in place. For example, if we consider a slice where the sulfate was defined with the help of gamma, now if it's fully saturated, the only thing which changes is it changes to gamma saturated. But you know that, for example, when we deal with dams where the seepage is happening, the pore pressure plays a very important role. So in SoilWorks, what you can do is that you can create the model in seepage, run the analysis, get the pore water variation in the model. Now take that pore water variation from that model, create the model in slope and apply it as a external load in case of slope stability. And thus you can more effectively check the influence of pore water variation on slope stability analysis. So it helps you check your model from this point of view. For example, most of the time the pore water variation is not at all considered if you are not going for the seepage slope coupled analysis. So that can also be considered in SoilWorks. So is soft ground slope coupled analysis. For example, if you have created a model in soft ground is basically a module devoted for consolidation. You can get the results from there and you can check that with each stage how the factor of safety is changing as a result of consolidation. So you can check that too. Next is the limit equilibrium. In the limit equilibrium method in SoilWorks, you can define composite failure definition. You have different methods like arc failure, polygonal failure, auto search failure options. So you can consider that for the definition of arc failure. Then the reinforced definitions you can define in LEM method. You can consider nail, pile, anchor, fabric. Yeah, you can do it in SRM, but many times in LEM you have to consider it as how it is going to consider that force while considering the equilibrium condition. So this kind of reinforcement can be considered while you are dealing with LEM. Then you have the LEM analysis method. So simplified and advanced analysis methods are available with detailed slice-wise calculation for manual verification, as I showed. And I already showed you that simplified methods like Bishop, Felenius, Janbu, as well as the advanced method like Spencer, Monkston, and Price Sharma are also available with SoilWorks. So next, report generation. So a high quality report is automatically generated by the program. So just helping you or providing you with the basic report generation for your model. Okay. So with this, I'll just like to summarize today's webinar. So today's webinar, I mostly focused on basically the analysis method and a brief introduction. So today you learn about the importance of different types of analysis, which is LEM, SRM, SEM. What is the importance of semi-coupled analysis, considering consolidation and pore pressure, and the relative ease in using the MIDAS products to simulate the problem. Okay. So for the next webinar, we'll be taking an example, the practical application, which is the economical design of slope. Now here what we'll be doing is that our problem statement is such: a slope is to be designed on a weathered rock using landfill layer. Okay, but to use some waste soil or recycled soil, a 1 meter stretch of waste soil was used. Now looking into the environment aspect, the designer agrees to use waste soil and use nails to strengthen the slope to obtain a factor of safety of 1.75. The method which we'll be using is SRM, that is the finite element method, strength reduction method. Now using nails, he's asked you to design the slope for us. Now we have to come up with the most economical design for slope without compromising on the factor of safety. So we'll be dealing with this problem in our next session, and we'll also be providing you with a manual tutorial for the same, that how we proceed for the same. Okay, so with this I'd like to conclude today's presentation. Thank you very much to all of you for attending this webinar. For any further queries, you can contact us at techsupport@midasit.com. The next webinar, that is on practical application economical design of a slope, will be on March 11th, same time. Okay, as per Indian it's 3 p.m. and as per UAE time it's 1:30 p.m. So with this I would like to conclude this session.